In this video, we're going to see that there's a natural transformation from vector spaces to double dual spaces. So let's fix a field K. And for any vector space V over K, let's define the dual of V, which is all of the linear one forms or linear functionals on V. That is all of the mappings from vectors in our vector space to values in our field K, such that this transformation is linear. It turns out that we can actually refer to V star as the dual space of V, because V star actually constitutes a vector space in itself over K. So for this to be true, we would of course need both vector addition as well as scalar multiplication defined on these functionals. So what would it mean to apply a function f plus g to a vector v? Well, we would just take the most natural option, which is to add up the results of f of v and g of v. And what would it mean to apply a scalar multiplication where c belongs to the field K? Well, we would just bring the scalar inside, multiply it by our vector, where this is defined in our regular vector space V, and f applied to the result of that. Using these definitions, it's not difficult to establish that V star, the dual of V, is actually a vector space over the same field K. However, this is a little bit tedious because we have to show each of the axioms for a vector space, so we'll leave that as an exercise. And instead, we'll establish that the precede by transformation T is actually a linear transformation in V star. So we know that if T is a transformation from a vector space W to a vector space V, both defined over K, then precede by T applied to some linear functional on V star is going to simply be F after T, which is going to be in W star, because before we apply T we're in W, and after we apply F we're in K. So precede by T is a function from V star to W star. And in order to show that it's linear, we need to take f and g, linear functionals on V, as well as a constant or a scalar in K, and we need to show that precede by T of f plus g is equal to precede by T of f plus precede by T of g. And we need to show that if we multiply precede by T of f by c, that we can move the scalar inside and get precede by c times f. So we can start with the top version. If we apply precede by T to f plus g and apply that to a vector v, then we can apply the definition of precede by to get f plus g after T of v. But this is simply f plus g applied to T of v, which is, by the definition here, f of T of v plus g of t of v, which is precede by t applied to f of v plus precede by t applied to g of v, which is the first result that we needed to show. Now for the second condition, if we take precede by t of f applied to a vector v, and we multiply it by a scalar c from k in front, then we get that this is equal to, by applying the definition of precede by, f after t of v, which is simply c times f applied to t of v, but that is just equal to precede by t applied to c times f applied to v, which was the second condition we needed to show. So based on those two conditions, we know that t precede by is a linear transformation on our dual space of the vector space V star. So based on that discussion, we can now conclude two things. One is that V star is a vector space over K called the dual space. And two, that precede by T is a linear transformation in V star where T goes from some other vector space W into V. But then we're going to apply a pattern that you'll see very commonly in category theory, which is to sort of fold things in on themselves or to apply certain conditions to themselves. So in this case, we know that the dual space is a vector space, so why not just take the dual of the dual space? We know this is a vector space, so this is a perfectly fine thing to define. And not only that, but we also know that since this is just the dual of a vector space, we also have that the double dual, as we'll call it, is also a vector space. So we'll call it the double dual space, and we can just write it as 2 stars without any parentheses. And precede by T is a linear transformation on V star, so we can use precede by on this linear transformation. We don't have to worry about the fact that it itself is already a precede by function. We just apply precede by to our transformation that we know is linear, and we know that this precede by, or T double precede by, is a linear transformation on this space this time, the double dual. We can therefore use this to define a functor so take the functor D from the vector spaces over K to the vector spaces over K, defined by D applied to a vector space V is going to give us the double dual space, which is also in vect K, and for any linear transformation T going from a vector space W to V, we have that D applied to T is going to be double precede by T. And we're going to show that there's a natural transformation from the identity functor, which of course just maps everything to itself, all objects to themselves and all morphisms to themselves, to this, what we might call the double dual functor. So if we draw this out to get a better picture, here we have our category vect k on the left and our same category vect k on the right. We have a linear transformation T going from a vector space V to a vector space W, both defined over the same field K. Our identity morphism is obviously very simple, just maps T to T, V to V, W to W. And our other functor D maps V into the double dual of V, W into the double dual of W, and T to double precede by T. So, in order to get a natural transformation, we need some sort of collection of mappings, each one going from a vector space to its double dual space. Call these lambda V, lambda W. We need to have that this chain commutes with this chain. That is lambda W after T is the same thing as T double precede by after lambda V. It turns out there is such a function from a vector space V to its double dual V star star for any V, which we will call eval for V. So eval for V of a vector V will give us back the evaluate at V function for that vector V, where the eval at V function goes from the linear functionals on V, V star, into our field K, and is defined by eval at V of F is equal to F of V. So it's important not to get these confused. This is eval for V. That is, we want to get the evaluation function for this vector V. And this is evaluate at V. That is, simply apply whatever linear functional the function is taking to the vector that function is fixed for. The first thing to note is that this function is properly defined in terms of domains and codomains to be a component of the natural transformation that we were looking at. So we see here that we're taking in vectors in V, so the domain is correctly the vector space V, and we're returning a linear functional defined on the vector space of linear functionals. That is, we're taking in a linear functional on V, and we're returning a value K in the field K. So this is a linear functional in V double star. Next, we need to show that evaluate for V actually does satisfy the commutativity property that we were looking at in the visualization of the natural transformation. So to make the writing a little bit easier, let's call this evaluate for capital E with a subscript for the vector space that it's defined on, which takes in a vector V in that vector space. And let's call evaluate at V lowercase e, which takes a subscript for the vector that it's defined on, and is applied to linear functionals on V. So what we need to show is that evaluate 4 defined on the vector space W followed by T is equal to double precede by T followed by evaluate 4 defined on the vector space V. So to show that this is the case, let's take a vector V in the vector space V. Well then, evaluate 4 on the vector space W after T, all applied to our vector V, is going to be simply the evaluate 4 applied to T of V, but then that's simply just the evaluate function at T of V. Next, if f is any linear functional in V star, then we get that the evaluate at T of V applied to our functional f is equal to f applied to T of V by the definition of evaluate at, which equals, well, this is just V having f after T applied to it, so we can call this evaluate at V of f after T, which is equal to the evaluate at f function applied to precede by T applied to f. We just move T in front and put a precede by, which is equal to the evaluate at f function followed by precede by T applied to f. And so all of this gets us that the evaluate at T of V function applied to f is the same as the evaluate at V function followed by precede by T applied to f. So we can combine the two results above in the following way. If we take eval 4 on the vector space W after T applied to our vector V, then we get that this is equal to evaluate at T of V by this equation, which by this equation is equal to evaluate at V after precede by T. But this is just double precede by T applied to this function, evaluate at V. But this is the same as eval 4 applied to that vector, V. And this is simply composition. So we can write this as double precede by T after evaluate 4 vector V. But then we get that evaluate 4 defined on W after T is equal to double precede by T after evaluate at V on vector space V, which is the exact result we needed. That's QED. And that proves that there's a natural transformation, evaluate 4, going from the identity functor to our custom functor for the double dual space.